Okay, then welcome everyone. Welcome to the ninth session for the polymer reaction engineering problem solving session for assignments 9. So we'll be going through a few problems which will be helpful in your upcoming assignment and the upcoming course material. Starting from the first question, if a person wants to prepare high impact polystyrene and acrylonitrile butadiene styrene copolymer using a combined bulk bead suspension polymerization, the water and dispersion should be added dash the phase inversion of the monomer solution. Then the step of water and dispersant addition is required to dash. Choose the correct options. So we have been given four options here. Uh, so first of all, we have to manufacture the high impact polystyrene and acrylonitrile butadiene copolymer in combined bulk suspension process. Bulk bead suspension process. So what is happening in bead suspension polymerization is that the monomer, when it forms the polymer, the polymer forms a smooth bead and it separates out and it is soluble in the solvent itself. So solution of polybutadiene in styrene or acrylonitrile is first of all required. So that's why polymerization of styrene acrylonitrile is initiated and continues under stirring until the phase inversion is occurring. So phase inversion is an important process. So that's why the water and dispersion should be added after the phase inversion of the monomer solution. So that's why the first blank will be after the phase inversion of the monomer solution. For the second blank, in the final stage, what happens is water and dispersants are added to the system and the polymerization is completed in the system. Why water and dispersants are added is that dispersants will suspend the polymerization. So we have to separate them out since the smooth beads are formed after the polymerization process. So these beads, they don't coalesce and fall back together. So for that purpose, what you need to do is you have to disperse them. So that's the exact reason why water and dispersants are added in addition to suspend the beads properly in the solvent. So that's why the two blanks are, first blank is after the phase inversion of the monomer solution, and in the second blank it will be suspend the polymerized beads. Second question. In semi-continuous and continuous emulsion polymerization, sufficient free emulsifier is usually required to dash. Choose the correct options. So for homogeneous, you can see right here that to nucleate new particle form, to stabilize the oligoradicals that precipitate in the aqueous phase, to saturate the surface of the existing interfaces and form micelles, or to increase the presence of available free monomers, resulting in ease of regulating the polymer characteristics. So the given scenario is that it's a semi-continuous and continuous emulsion polymerization process, and sufficient free emulsifier is added. So what is the reason why it's happening is uh, for homogeneous nucleation process to occur, there should be sufficient free emulsifiers available to stabilize the oligoradicals that precipitate inside the aqueous phase. So precipitation of oligoradicals is like very is the process which is going on, and to stabilize that process, you need to add the sufficient free emulsifiers because it will result in homogeneous nucleation of the polymers. So the nucleation sites for the polymers to grow will be homogeneous since the formation of oligoradicals is taking place. So to stabilize these oligoradicals that precipitate in the aqueous phase. And another scenario is that for heterogeneous nucleation to occur, there should be sufficient free emulsifier available to saturate the surface of the existing interfaces. So when you have the existing interfaces and you have heterogeneous nucleation going on, means heterogeneous surfaces are there and nucleation sites are available on them. So in that case also sufficient amount of free emulsifier is required for heterogeneous nucleation on the existing interfaces, particles or monomer droplets. That is the existing interfaces which forms the micelles. So here for the single blank, there will be two answers: to stabilize the oligoradicals that precipitate in aqueous phase and to saturate the surface of existing interfaces and form micelles. These two are the correct answer for this question. Third one is choose the correct characteristics of bead suspension polymerization from the following options. So four options are: in bead polymerization, the polymer is soluble in its monomer. Next, in bead polymerization, the polymer is insoluble. Third is the resultant bead will be porous and irregular. Fourth is the resultant bead will be non-porous and smooth. So, by definition of the suspension polymerization, and we have already seen uh, it in the previous classes also, that in bead polymerization, the bead polymer is soluble in its monomer. So, it will be easily dissolved in the monomer itself. On top of that, when the bead separates out, the polymer bead separates out, it is non-porous and extremely smooth. That is the exact reason why it is called a bead polymer, because it forms a proper smooth spherical surface, and that is why it's non-porous and smooth. So the answer for this question is the first point and the fourth point are the correct. In vinyl chloride monomer, VCM suspension polymerization, overhead reflex condenser is used for the effective heat removal from the polymerization process. By increasing the reflux rate, the porosity and particle size density of polymer should dash. Non-condensable gases can get trapped in the condenser due to reflux. The trapped gases can trap. So, increase, decrease, reduce the heat removal efficiency, interact with the polymers, and affect its morphology. So, during the vinyl chloride monomer suspension polymerization, overhead reflux condenser is used for removal of the heat. So removal of the heat is the uh, main purpose of the overhead reflex condenser. Increase in reflux rate will result in high purity. So what happens is by increasing the reflux rate, you're basically the porosity, particles size, density of the polymer should increase because the purity of the entire polymer batch will be increased. So that's why first blank is increases. The porosity and particle size density of the polymer should increase. Next is non-condensable gases can get trapped in the condenser due to reflux. The trapped gases can. So non-condensable gases, what they do is that they hinder the heat removal because they don't condense and they don't eject the phase change heat. So we know that phase change occurs when there is a removal of latent heat. So that's why they remove the uh, heat removal efficiency because since they are not condensing, the latent heat is not removed and the heat dissipation is not good. So non-condensable gases can get trapped in condenser due to reflux. The trapped gases can reduce the heat removal efficiency. So the second blank is reduction of the heat removal efficiency. Next one, when the relative velocity is similar to that needed to make a drop slightly unstable, a number of tiny droplets are separated from the original. This drop breakage condition is referred to as. So, the scenario where this is going, where the context is that the particle size distribution during the polymerization process, that is the scenario which has been depicted here, and the relative velocity is similar to that needed to make a drop slightly unstable. So when the impellers are used and turbulence is created inside the polymerization system, the relative velocity, which is achieved by the drops, make them unstable, or a number of tiny droplets are separated from the original one. So what kind of breakage phenomenon is happening? So this is with respect to the particle size distribution. The relative velocity is similar to that needed to make a drop slightly unstable. Number of tiny droplets are separated from the original one. This is a classic example of the erosive breakage. So what happens in erosive breakage is that you have a single drop, it becomes unstable, and then it breaks up into smaller droplets, uh, smaller droplets. And the other types of breakages are, first, as you can see here, first is thorough breakage. In thorough breakage, what happens is you have a single drop, it expands homogeneously on all sides, and then it distributes itself into different drops. There is no instability happening. In erosive breakage, what happens is that there is an instability of them. So I can show you a slide demonstration right here. So in erosive breakage, what happens is if this is your drop, uh, then the next step, because of the higher relative velocity, is that it starts becoming very unstable. Once it becomes very unstable, the next step is that it starts breaking up into small droplets. So you can see that the big drop is first becoming unstable, slightly unstable, and then it undergoes breakage to form the small droplets. This is the erosive breakage, and that is the correct answer for this one, as the statement above is describing the erosive breakage. Now let's go to the thorough breakage. For additional information, let's explore the other options also. First one is the thorough breakage. What happens in thorough breakage is that you have a droplet, uh, and then what happens with this droplet is that it expands without any instability, and then it quietly separates out into small droplets. So there is no instability in the big drop itself or something. So that is the kind of drop breakage mechanism in the thorough breakage process. Next we have the coalescence prevented by the continuous film. So that is the third one. That is liquid film prevented coalescence. What happens in this is you have two drops which are trying to merge together, but what happens is there is a film present in the middle of them. That film is kind of preventing the coalescence, but in the long term, you can see that once the two drops are combined, they will form the bigger drop. So these droplet breakage and formation mechanisms are very important to understand how the polymer molecules are formed when the entire relative velocity concept is brought into the turbulence of the polymerization process. Then last one here is the immediate coalescence. In immediate coalescence, what happens is the moment these two drops are encountered, uh, excluding the film in the middle, they both combine quickly and form the big drop. So these are the four types of droplet breaking and coalescence processes. But here you can see that the process which describes the statement given in the question is the erosive breakage. Moving on to the next question. For population balance modeling in suspension polymerization process, consider a case where two drops are colliding and a continuous phase liquid film is stuck between the two drops, which stops them from coalescing. For draining the liquid film, the blank energy of the trigger drop oscillation must be greater than the energy of the dash between the drops. The drop length is interrupted until the liquid film is fully drained. So first we'll analyze the entire statement which is given here. We are checking the population balance modeling in suspension polymerization process. So in suspension polymerization process, as the monomer beads are uh, becoming the spots for the polymerization process, the population balance modeling of the entire process is occurring. And here two drops are colliding and a continuous phase liquid film is stuck between the two drops. So we know that this is a classic case of the coalescence prevented by the continuous flow. So we saw in the previous question, liquid film prevented coalescence. There is a small film between the two drops and it is preventing the drops to combine. So liquid film is stuck between the two drops, which stops them from coalescing. For draining the liquid film, the dash energy of the trigger drop oscillation must be greater than the energy of one. So what happens is that after initial collision of the two drops, continuous phase liquid film is stuck between the two drops, which stops them from coalescence. So in that case, what should be higher is that the kinetic energy of the trigger drop oscillation must be greater. Why? Because if the kinetic energy is higher, it will impact the liquid film faster and it will be able to break or separate out the liquid film much more in a much more better way.
Sorry, it
So,
got disconnected between it connected back.
yeah, it's okay. It's okay. No problem. So, I'll explain this part once more. So, consider a case where two drops are colliding and a continuous phase liquid film is stuck between the two drops. So, what is happening here is that the kinetic energy of the drop should be very high, so that what happens is that the film, the moment the drops come together, the film should collapse. When the film collapses, these two drops will coalesce and form a single droplet together. So that's why the first blank is the kinetic energy of the trigger drop oscillation. Kinetic energy must be greater than the energy of the adhesion between the drops. The drop length is interrupted until the liquid film is fully drained. So what happens is, so the second part of this phenomena is that the drop oscillation will be greater than the energy of the adhesive forces between the drops. Why adhesive forces is that because if the impacting energy, kinetic energy is high, they will come together, and if the adhesion is happening, if the drops stick together, the liquid film will only partially break apart, and the drop length is interrupted until the entire liquid film is. So to drain the entire liquid film, the adhesion energy between the drops, uh, the kinetic energy of the drop oscillation must be greater than the energy of the adhesion between the drops. So the drops should like momentarily come close together, break the film so that it drains out, and then they must again come back together to coalesce together. So the first blank answer is kinetic, the second blank answer is adhesion. That is the first option. Next one. Statement 1. An increase of the dispersed phase velocity eta d results in a reduction of both breakage and coalescence rates. Statement 2. If we increase the input power per unit mass, that is, increase in agitation speed and suspension polymerization, the drop coalescence rate will increase. So, what is the correct answer? So, for this effect of the what happens here is that the effect of viscosity of the continuous and the dispersed phases on particle size distribution. So what happens is that the the dispersed phase viscosity eta d, increase of the dispersed phase viscosity eta d results in reduction of both breakage and coldness. So whenever the dispersed phase viscosity increases, the both breakage and coalescence rates will reduce. Why? Because since the entire dispersed phase viscosity is very high, the movement of the droplets will be hindered. So the movement of the droplet either to coalesce or to break will be reducing. So that statement one is true. Statement two is if we increase the input power per unit mass, example, increasing the agitation speed in suspension polymerization, the drop coalescence rate will increase. So what will happen in this is that, for example, if you are increasing the impeller speed or the agitation speed in suspension polymerization is that you are externally providing enough force for the droplets to combine together or coalesce together. To hold up fraction of the dispersed phase decreases the turbulent intensity. So what happens in this case is that the drop coalescence rate will definitely increase because the impaction between the different drops will be higher since the impeller speed has been increased. So statement one is true and statement two is also true. In suspension polymerization, the increase of folded fraction of the dispersed phase decreases the turbulent intensity. So folded fraction here means that uh, what does the term folded fraction here mean? Fraction of the dispersed phase versus the dispersion rate. That is the Holder fraction of the dispersed phase decreases the turbulent intensity. So the turbulent intensity, because of which the drop, coalescence, and breakage is governed, the increase of the Holder fraction of the dispersed phase will definitely decrease the turbulent intensity. So if the dispersed phase drops are being held back either with increase in viscosity or the unit you, the energy input power per unit mass is low or high, that will definitely affect the turbulent intensity. So it's true. That's why increase of Holder fraction is decreasing the turbulent intensity of a system in suspension polymerization process. What is the characteristic that affects the weatherability and resistance to hydrolysis of emulsion polymer copolymer? So what happens in this is that weatherability means if any polymer, if you are subjecting it to any environmental factors such as humidity, heat, ultraviolet radiation, or any kind of mechanical torsion or flexing, uh, whatever may be. So that kind of characteristic, what is the characteristic that affects the weatherability and resistance to hydrolysis? Hydrolysis will occur when there is moisture present in the atmosphere, or if the emulsion polymer copolymer form is subjected to any kind of water treatment, or if any presence of humidity is detected. So in that case, copolymer composition will affect the resistance to hydrolysis and directly affects on the glass transition temperature. The glass transition temperature will be shifted because of the hydrolysis phenomenon. Why? Because presence of water between the polymer molecules, because of the free volume space whichever is present there, the humidity will accumulate or affect in such a way that the copolymer composition itself will be governing how the glass transition temperature is affected. And the shift of glass transition temperature itself can determine how the polymer itself is going to behave and what kind of property shift it will be experiencing because of the hydrolysis, and which will result in poor property of the emulsion polymer. So that's why copolymer composition is very important to be taken into account to check the weatherability and resistance to hydrolysis for a emulsion polymer or a copolymer. So copolymer composition is the correct answer for this. What is the characteristic that affects the shear and peel resistance to hydrolysis of emulsion copolymer? So first one was that the weatherability and resistance to hydrolysis. Second one here is the effect of shear and peel resistance to hydrolysis. So because of hydrolysis, the shear and peel resistance, how they are affected, which factor will be responsible for that? Now, in this case, we can see that going back to the first class, when we were talking about the molecular weight of the polymer and the workability or the processing related to the molecular weight, the higher the molecular weight, the higher the difficulties in processing of the polymer. So in that case, so
Yes, Rahulji. Yeah.
yeah, so the characteristic that affects the shear and peel resistance to hydrolysis, we know that molecular weight distribution of a polymer is very much important in describing how the mechanical properties of a polymer are affected. So shear and peel resistance are directly related to the mechanical flexing, torsion, any kind of behavior which is involved in that. Because we are forcefully removing the polymer or breaking the polymer bond itself. So that's why the chain dynamics, which comes due to the molecular weight distribution, are mainly responsible for the effect of shear and peel excitation stage and finally react with the second compound to generate free radical is called photoinitiation. So this is not correct because the correct term for this is the compound which absorbs desired amount of energy and get excited to generate free radicals is called a photosensitizer. So these are not called photoinitiators, they are called photosensitizers. So the desired amount of photo energy is absorbed by the photosynthesizer and it starts generating the free radicals. So this statement is false because it's not called photo initiator, it is a photosynthetizer. Kinetic chain length can be defined as the ratio of the following options. So here we have given three options: polymerization rate by initiation rate, polymerization rate by termination rate, initiation rate by termination rate, or none of the above. So first of all, what is kinetic chain length? Kinetic chain length is the number of monomer units reacted with an active center during initiation to the termination state. So from starting from initiation to termination, the number of monomer units which have reacted with an active center give the kinetic chain length during the polymerization process. And this can be written by the expression of rate of polymerization divided by the rate of termination. So that's why correct answer for this question is option B, that is polymerization rate divided by the termination rate. Because all the monomer units which have reacted with an active center during the initiation to the termination is the entire polymerization step. So polymerization rate divided by the finite process, which is the termination rate, will give you the kinetic chain length of a polymerization process. In suspension polymerization, the average rate of energy.
Termination only, na? Termination is the correct time.
Yeah,
Polymeration
termination.
is termination. Okay.
Polymerization, yeah.
Yeah.
In suspension polymerization, the average rate of energy dissipation, epsilon, is used to characterize the quality of mixing. In the presence of a dispersed phase, the turbulent intensity blank due to the blank in the velocity fluctuation of continuous phase. Select the correct option. So the mixing phenomena usually controls the particle size density. So the better it is mixed, the higher and better particle size density will be forming. So in suspension polymerization, the rate of dissipation is characterized by the quality of mixing. So the presence of any dispersed phase that during the turbulent intensity decreases. The dispersed phase decreases due to the turbulent intensity, and because of in dispersed phase, turbulent intensity decreases due to decrease in velocity fluctuation of continuous. So there are dispersed phase and the continuous phase. So since there are fluctuations in the velocity of the continuous phase, the turbulent intensity, the dispersed phase, the turbulent intensity decreases due to the decrease in the velocity fluctuations of the continuous. So both terms are decreasing. So that's why the correct answer for this is the fourth option. That is, both of them are decreases and decrease. Dispersed phase, in the presence of dispersed phase, the turbulent intensity decreases due to the decrease in velocity fluctuations of continuous. Which of the following types of monomers cannot be used in plasma polymerization for the formation of cross-linked polymers? Alkanes, cyclic or ring compounds, unsaturated hydrocarbons. So for a standard polymerization, polymerization process, none of these can be used since they are not suitable to be used with the plasma, as plasma is a very high temperature polymerization reaction, and alkanes, cyclic compounds, or unsaturated hydrocarbons can create unwanted byproducts during the plasma polymerization. That's why compounds which can withstand very high temperatures are only required for the plasma polymerization process. So none of the above is the correct answer for this. During chain transfer reaction in radical polymerization, the telomerization of polymer occurs. So during chain transfer process, if the rate constant for the transfer reaction is very large, then that of the propagation, while the rate of reinitiation is comparable with the original propagating radical. So in this case, what is happening is when the rate constant for the transfer reaction is very large, then that of the propagation. So it is quickly transferring before it is propagated. So the activity of the chain is transferring before the chain can propagate also. while the rate of reinitiation is comparable with the original propagating radical. So the original radical which was propagating because of the chain transfer, its rate is equal to the reinitiation which is occurring. Reinitiation means formation of new radicals which are initiating the polymerization in other spots. So there will be no effect on the rate propagation itself, but chain length will change drastically and small polymers. Since the chain transfer reaction is very fast, it is not able to propagate properly and it is forming small chains. And because of that, this phenomena is called the telomerization, of the polymer. So during polymerization, the chain transfer reaction is very high. At that time, the telomerization process occurs and small polymeric chains are formed. So this happens when the transfer rate is much higher than the propagating rate, and the you can see right here, option number B is the correct answer, where KTR, that is the transfer reaction rate, is much higher than the propagation. And we have here Ka is equivalent to the Kp, that is the propagation. So here the initiation radical reaction rate will be equal, reinitiation radical reaction rate is equivalent to the original propagating rate. So that's why option B is the correct answer. KTR is greater than Kp and Ka is equal to Kp. So this is the second option is the correct answer. In radical polymerization, sometimes the premature termination of propagating polymer occurs due to the transfer of hydrogen or other atoms to the propagating polymer from the same molecule, solvent or with the initiator. The new radical formed due to the chain transfer reaction can again initiate the polymerization. This leads to what? So we have four options here. In premature polymerization, one second. So in premature termination of the propagating polymer, which happens, which leads to the decrease in molecular weight of the final product. So there is a decrease in the molecular weight of the final product as compared to the theoretically determined value. So in radical polymerization, if there is premature termination occurring, so the theoretical value of the molecular weight which was expected will not be achieved, and lower value than the theoretical determined value will be formed in the product. So reasons why this happens is because of the transfer of hydrogen and other atoms to the propagating polymer from same monomer, initiator, or solvent. So decrease in the molecular weight of the polymer is the correct answer for this question, since the polymeric reaction rate is reduced. I see that Partha has joined us now, so I'll go through the questions once again. Uh, Sir has observed it, like all the questions. So if you have any other doubt, like sir, if you have any doubts, you can ask me, or else I'll start explaining Partha question.
No problem here. Please go ahead. Because actually I was noting all these things. Only I had one doubt, very specifically with respect to this one only,
Hmm.
where chain transfer agents, like where we are having additional radicals, like free radicals ready to give, right? That only we are considering here.
Huh.
That is the justification for this three, no? Option three options.
Hmm. Okay. Okay then. Yeah, yeah. There are only three options. Yes.
Okay, okay. That much only other things are clear. And the next one is related to, okay, that is polymeration, bead polymeration,
Yeah.
powder suspension and powder related aspects.
Hmm.
Right. Okay, this is clear.
So, like, if you just go through the sir's notes, right, you will be able to understand all of this. Because these are only the process
Yeah,
details.
probably I think here this is for the coming for the upcoming week, I believe.
Yeah, yeah. This is for the
Yeah, okay, okay. Otherwise, other things are understandable. Whatever that you discussed is good.
Hmm. Yes. Okay, then I'll just go through the questions
Shall
once
I
more.
take leave here? Actually, there is one more session,
Yeah,
if
yeah,
you don't mind.
yeah, yeah, sure,
Thank you, thank you,
sure.
thank you.
Yeah. Oh, okay then. So starting from the first question, which of the following compounds are considered as chain transfer agents for the redox initiation process? So first of all, what are chain transfer agents? Chain transfer agents are agents which transfer the activity of a propagating chain to the other chain. So this happens, and why is this required is because when you want to uh, control the rate of polymerization and you want to control the molecular weight of the polymer form, this is a very good way to control it, as you won't let the chain to propagate at a very high molecular weight, and you can just transfer the activity to the other monomer. So that's why the compounds which are considered as chain transfer agents for redox reactions are amongst these methylamine, aliphatic alcohol, and mercaptans, because they are easily able to transfer the free electrons to uh, other propagating chains. They are very capable in transferring the free electrons, as they themselves are having quite an abundance of electrons which are present there. So that's it. That is the exact reason why the first three are suitable for the redox initiation process. Now, redox initiation process is the initiation process where the polymerization process is initiated relying on free radical producing the oxidation reduction reaction. So that is the redox initiation process. So in that, methylamine, aliphatic alcohols, and mercaptans are used as popular transfer agents for redox initiation. This is a quite normal question, because these are just the few examples of chain transfer agents for redox initiations, and you can quite easily identify them from the electronic configuration and how they are able to transfer the electrons to the other propagating chains. If you read about the chain transfer agents and the redox initiation process. In the blank suspension polymerization, the polymer is insoluble in its monomer and thus precipitates, contributing to the formation of irregular grains or particles. So we know that suspension polymerization has two types: powder and bead. So in bead polymerization, what happens is bead polymer is soluble in its monomer and it forms smooth spherical particles. Hence the name bead, because the since it is soluble, it will form smooth particles and it is bead shaped. And since it's not irregular or grain. So the remaining one only is the powder suspension, where the powder is insoluble in its monomer and thus the precipitate contributing to the irregular grains is formed. So that's why powder suspension polymerization is the answer for this question. Statement 1. Chain transfer agents in redox initiation are helpful in the case where molecular weight of the product is to be controlled. As I said in the first question, chain transfer agents in redox reactions are usually used to transfer the activity of one chain to the other, and hence it is able to stop the propagating of the single polymer chain to a very high degree, and we can easily control the molecular weight. Statement 2 is chain transfer agents result in retardation uh, re- retardation in the rate of reaction. This is also true because since uh, the activity of one chain is being transferred to the other, the fastness of the reaction, or the how fast the reaction is occurring, is also hindered because of this. So that's why the rate of the reaction is also affected in a negative way. So that's why chain transfer agents will result in retardation of the rate of reaction. So statement one is correct, and statement two is also correct for this one. Next we have is dispersion polymerization usually yields polymer particles with sizes in between those obtained by emulsion and suspension. So if you know about the emulsion polymerization and suspension polymerizations, we clearly know that emulsion polymerization, the particle size lies between 1 to 10 micrometers, and the the suspension polymerization is between 10 to 100 millimeters. So somewhere in the middle of that will be the 1 to 10 millimeters. That is the particle size produced in the dispersion polymerization. So that is in the middle of emulsion and suspension polymerization. You will be able to find the answer for this question just by going through the initial descriptions of the emulsion and suspension polymerization process. So because of this, the correct answer for this is 1 to 10 millimeters. The compounds which absorb the desired amount of photoenergy to reach its excitation stage and finally react with the second compound to generate free radical is called a photoinitiator. So the entire statement is correct except the fact that it is not called a photoinitiator, it is called a photosensitizers. And photosensitizers absorb the desired amount of photoenergy and get excited to generate free radicals. So once it reaches the excitation stage, it will start generating the free radicals. So this statement is false because it's not photoinitiator, it is called photosensitizer. Kinetic chain length can be defined as the ratio of. So we have been given three options right here. So first of all, we'll see what is kinetic chain length. Kinetic chain length is nothing but the number of monomer units reacted with an active center during initiation to the termination step. So what happens in this is that if there is an active center and if a monomer reacts with it and subsequently many monomers react with it, and if their activity is monitored from the initiation to the termination, that will give you the and the chain formation how of the monomer, if you are going to judge it, that is the kinetic chain length of that polymerization process. And since that is the definition for the kinetic chain length, from there itself you can point out that the polymerization rate divided by the termination step rate will give you the kinetic chain length of a polymerization process. So option number two, if you can see, polymerization rate divided by the termination rate is the correct answer for this question. In suspension polymerization, the average rate of energy dissipation epsilon is used to characterize the quality of mixing. In presence of a dispersed phase, the turbulent intensity due to the dash in the velocity fluctuations of the continuous phase. Select the correct option sequentially. So in suspension polymerization, what happens is the average rate of energy dissipation is used to characterize the quality of mixing. Now, why do we need to do that? That's because mixing phenomena can control the particle size density. So if you are able to control the particle size density through the average rate of energy dissipation, which is used to characterize the quality of mixing, that will be very helpful in maintaining the molecular weight and controlling it throughout the polymerization system. And because of that, it determines the flow and energy field inside the vessel. So because of this, we are able to easily tell that what is the energy dissipation parameter inside the vessel. So when we, in the presence of a dispersed phase, the turbulent intensity will decrease due to the decrease in the velocity fluctuation of continuous phase. So that is what is happening. So when there is a dispersed phase, in presence of a dispersed phase, the turbulent intensity will decrease, will decrease due to the decrease in the velocity fluctuations of the continuous phase. If there is a decrease in the turbulent intensity of the dispersed phase, which can be attributed to the decrease in the velocity fluctuation of the continuous phase. Which of the following types of monomers cannot be used in plasma polymerization for formation of cross-linked polymers? So in plasma polymerization, you need polymers at very high temperatures In plasma polymerization, uh, the temperature is very high for the cross-linking of polymers which are required. And that is the exact reason why alkanes, cyclic or ring compounds, and unsaturated hydrocarbons, which are mentioned right here, cannot withstand that kind of agitation, and they are not suitable for this kind of cross-linking process. So that is the exact reason why none of these are suitable for the uh, reaction, plasma polymerization reaction. During chain transfer reaction and radical polymerization, the telomerization of polymer occurs. Now, first of all, we need to understand here we can see that there are different terms being used here: chain transfer reaction and radical polymerization, and telomerization. Chain transfer, we know what is chain transfer. Chain transfer occurs when the activity of one chain is given to the other chain. The active center of the one chain is given to the other chain to stop the propagation of the first chain. And what is telomerization is that when during the chain transfer process, if the rate constant for the transfer reaction is very large, then that of the propagation, when the chain transfer constant is very large than the propagation, while the rate of reinitiation is comparable to the original propagating rate. So what is happening is that there are two processes here. The chain transfer coefficient, the chain transfer reaction coefficient being very larger than that of propagation, first. And second is that rate of reinitiation is comparable with the original propagating radical. There will be no effect on the rate of propagation, but the chain length will change drastically, and small polymers will the reason why small polymers are forming is the chain transfer coefficient is very high. So it is quickly jumping to the other monomers before it can grow up to a certain length. And that is the exact reason which is called telomerization, which means that it is forming small polymers and it is propagating rapidly. That is called telomerization of a polymer. So when does that happen? When the chain transfer reaction rate is greater than the propagating rate, and the reinitiation rate is equivalent to the propagating radical, original propagating radical. So which can be described by option number B. Option B, where KTR is greater than KP and Ka is equal to Kp. In radical polymerization, sometimes the premature termination of propagating polymer occurs due to the transfer of hydrogen other atom to the propagating polymer from the same monomer, solvent, or with the initiator. The new radical formed due to the chain transfer reaction can again initiate the polymerization. This leads to blind. So in radical polymerization, what happens is the process of premature termination of propagating polymer happens, which leads to decrease in molecular weight of the final product. So the molecular weight is decreased since there is premature termination. The polymer chain is not allowed to grow to its maximum potential. And when this is happening,